gamma squared. So this will be so we have a property defined for velocity now, or eta, where the Lorentz four-vector product with itself is always constant minus c squared. Plus c squared is constant, so it doesn't matter in what frame you calculate this, it's always minus c squared. Okay, does this make sense so far? Any questions? If not, then we can move forward. If we now have a good expression for the velocity, we can go to define a relativistic momentum. So in classical mechanics, non-relativistic, so non-relativistic, you had a three momentum P. What was the definition of the momentum? If you forget relativity for now, classical mechanics.
Mass times velocity.
Mass times velocity, exactly. mv. Okay. So that means we can try simply defining a form momentum as m times eta. Right? Would be the natural generalization of this. So what is that? That is mass times gamma times c and the three velocity. Okay, so that means we can write this as gamma c and so it's pretty clear that the three vector here is simply just our new relativistic momentum with the definition, with the difference now. Of course, the velocity never exceeds the speed of light, but what if you approach the speed of light? Can you still increase the particle's momentum, even if you never exceed the speed of light?
Mass.
The mass. You can essentially define something like a relativistic mass, that's Lorentz factor times n. Of course, if you remember gamma is 1 over square root 1 minus beta squared, you never get the velocity actually to become exactly c. So it's never exactly 1, beta is never exactly 1. But if you just increase beta a tiny little bit, you're already close to 1. The more you increase beta, the closer you get to 1, this gets closer to 0. 1 over something very small gets very large. So if you approach the speed of light, gamma gets larger and larger and larger. So even if you never actually reach the speed of light, you just get still a little bit closer to speed of light, you increase gamma, you can still increase the momentum. So there's no real limit to how large the momentum can be, even though you never get to go faster than the speed of light. And then we have something here, and this gamma mc, that is the time component of the momentum. And here, maybe coming back to classical mechanics, who remembers what Noether's theorem was? That's now one way to motivate what we put there in the time component of the momentum. Anybody remember from classical mechanics what Noether's theorem was? Noether's theorem said something about symmetry and a conservation law. If your space is just symmetric under translation, that means it doesn't matter if you do an experiment here or here. That means that's a translational symmetry. In classical mechanics, that directly gives you a conservation law. Which one is that? It's momentum conservation. So a space symmetry, symmetry in space components give you a conservation of momentum. Time symmetry gives you conservation of energy. So that's the motivation how momentum and energy are essentially related in terms of the 4-vector product as momentum, the 3-vector, and energy, the time component. But in terms of units, you figure out that you get the correct units of energy only if there's an extra factors. So the 4 momentum has always this form of energy over c, and the 3 momentum being gamma m. Alright, so now I've postulated something here. So from this, we have an important statement here that the energy of a particle is gamma mc squared. So let's start out. This is, of course, if anybody has ever heard anything about relativity, you know E equals mc squared, right? A lot of people know that. Few people understand what it actually means and where it comes from. So if we are at rest, so the particle is not moving at all, so beta equals 0, that means gamma is 1, right? So that means if the particle is at rest, it still has a relativistic energy that is mc squared. So that's, of course, Einstein's famous E equals mc squared. Now that's an energy that every massive particle always has, even if it has no kinetic energy whatsoever. And see that actually this is energy that can be converted into other forms. You've probably heard of matter, antimatter annihilation, electron-positron annihilation. The energy in this rest mass can actually be converted, say, into energy of radiations. So this is actually available energy. If you have an anti-particle, you can liberate that and transform it into other form of energy. Now let's further see if this kind of makes sense. So this is the rest energy mc squared. What does the energy then look like if we have a particle moving? If we're looking at the limit, probably better do that. Yeah. We want this to be in a non-relativistic limit. We have a kinetic energy. What's the kinetic energy if we forget relativity for now? In terms of mass and velocity?
Half mass and velocity squared.
1/2 mv squared, exactly. So let's see if we take our expression for the relativistic energy now in a low velocity limit, if we actually recalculate. We want this, of course, if we are non-relativistic, then we better agree with classical mechanics. Let's see if that works out. So if we say V is much less than C, meaning that beta is much less than 1, then Lorentz factor is 1 over square root 1 minus beta squared. What's the first order Taylor expansion now for beta much less than 1? Starts, of course, with 1, right? And then, remember, 1 minus beta, or 1 minus epsilon to the power n. First order was 1 minus n epsilon, right? N here is minus 1/2, right? And the square root of this, epsilon is beta squared. So this gives us minus gives plus 1/2 beta squared, right? So that means if we are in a non-relativistic limit, the energy as is gamma mc squared is gamma is then approximately 1 plus 1/2 beta squared mc squared. So that is mc squared plus 1/2 m and beta squared times c squared, isn't it? So that is nice. So we recover in the non-relativistic limit that the energy is just this rest mass energy that is always there as long as the particle exists, plus the non-relativistic kinetic energy. So again, we've verified that this really makes physical sense and we recover what we expect in the non-relativistic, what we know from classical dynamics. Okay, now let's maybe go on and calculate what is the 4-vector product of P dot D with itself. But you should know that now, since we know that P is simply just M times eta, right? And eta dot eta we have calculated, right? It's minus c squared. So it's minus mc squared. Okay, but we can also write this in terms of this form of the momentum vector. Right? So we can also write this as minus E over c squared plus 3 momentum squared. Right? Or we can write something that we call a dispersion relation that gives you the energy of a particle as n squared c to the 4th n squared c to the 4th plus c squared. So this is something that's often referred to as a dispersion relation. Okay, so we know how energy and momentum are related to each other just by this constancy of the 4-vector product. For massive particles, so you have this kind of funny quadratic behavior here. But when we're talking about light, everybody's heard light you can describe as little particles called photons, right? So for light, the particles called photons, with what speed do they move? These are light particles with the speed of light, right? So if they actually move with the speed of light, then, well, we'd rather not have an expression like this for the energy, because gamma, if beta becomes 1, you divide by 0, it becomes infinity, right? So this probably doesn't really make sense anymore. What is the only way to get this to make sense? If this becomes infinity, you can only do that if the mass is 0, so that you still end up with something finite. Right? So photons, if they move with the speed of light, they have mass equal 0. So if we set the mass equals 0 here, we know that the energy is simply related to the momentum times speed of light. So that also means that we can write the form momentum of a photon as just, well, this is simply E over C and P, C1. We know the length of P is the same as E over C. So let's say we simply write this in terms of some unit vector in which the photon is propagating, right? So with the definition of k dot k equals 1, it's a unit vector, and the 3 momentum just being in the k direction. Right? That's the way I'm doing this. Now, of course, if you calculate this 4-vector product, you get 1 minus 1 gives you 0. So from that, of course, here we're all done with this here. Then, of course, it follows immediately what is P dot P for a photon. That's P dot P. Calculated here, P dot P is minus m squared c squared. The mass is 0. Also, if we take this here, P dot P, get E squared over c squared, 1 minus 1. So we can actually write this out, E over C squared, and then you have minus 1 for the time component, plus Ck dot K, but that's of course 1, so this, right? So for momentum, vector product itself, for the photons, is always here. Okay, so far, makes sense? So we've introduced momentum vector, write this out, and then P as E over C and free momentum, where this was gamma and V for massive particles. For photons, the momentum has the same magnitude as the particles. Okay, we have a couple of minutes. We can start doing things that go a little bit more in detail and are actually much more straightforward than the way the textbook does it. But for anybody who's going into astrophysics, this will come up over and over again. So we're going to discuss how photon energies actually change if, say, they are emitted in one frame. So, say we have one frame here, say some x-axis here. We have one frame in which we emit a photon. Let's call this our emitters frame here. We emit a photon at some angle, theta, so which some energy E in the emitters frame. And we, just to save a little bit of writing, we call, so this theta in the emitters frame equals cosine theta. Okay, so that is one frame in which a photon, a ray of light, so is emitted. What we'll calculate is, considering that this frame now is moving, say, in the x direction with some velocity v. That gives us a beta equals b over c and some Lorentz vector gamma. This is moving with respect to another frame in which we receive this. So this is our receiver's frame, in which we see that photon that's emitted from this moving source. You know, of course, photon speed will always be the speed of light, but the energy might change. That Doppler shift, I'm sure you've all heard of the Doppler shift before. We'll now calculate it in the correct relativistic form. So, again, we'll have our x-axis here, and we'll see this photon coming in at, already giving away the answer a little bit, at some receiver's energy, at some theta in the receiver's. Of course, again, we say mu in the receiver's frame is cosine theta. Already seen in the movie, we watched the rest of it towards the end of the lecture today. Already seen that these angles may actually not be the same because we get this relativistic aberration, and we'll derive exactly what this relativistic aberration is. So now, bear with me for a few minutes to make some definitions that may not make too much sense right now, but you'll see that this actually is very, very useful. So, first of all, we have, of course, the form momentum of the photon in the emitter's frame. That's just E equals over C. And set here, so sorry, that is E emitter's frame over C, 1 and K emission frame. And we have the photon in the receiver's frame in a similar way, energy in the receiver's frame over C1 and receiver's frame. Right? Okay. Now let's define some 4 vectors for different velocities. And the main point on which we base everything is that 4 vector products like this will be the same no matter if we evaluate them here or here. That will be the main trick. So one very trivial, funny looking one is if we say in the emitter's frame, we figure out what is the velocity with which the emitter's frame is moving with respect to itself. Doesn't make much sense, does it? But let's just write it down. So this is velocity. This one's gone. So the velocity of the emitter's frame with respect to the emitter's frame. What is that? Remember, velocity vector was gamma 1b, right? What's the velocity of the frame with respect to itself? 0, right? And then gamma is 1. So that is a trivial vector of 1, 0, 0, 0, right? All right, but we can say what is in the emitter's frame, the velocity of the receiver's frame. That is, but now the receiver's frame is actually moving, well, with velocity minus beta here, right? So in the receiver's frame, in the emitter's frame, that has a velocity gamma 1 and minus beta. Okay? So that's the velocity of this frame with respect to this frame. We can do similar definitions here. So the velocity of the receiver's frame, or in its own frame, obviously again is the trivial time vector. But the velocity of the emitter's frame in the receiver's frame is, now it moves with positive x velocity, so is gamma 1 and beta. Right? Okay, so now, as I said, everything we do is simply based on Lorentz 4 vectors being invariant. So, evaluate in the two frames. We'll evaluate in the two frames. Let's say, for example, the velocity of the, which one we want first? This one, so of the emitter's frame dot the form momentum of the photon. So that is, calculate that first in the emitter's frame, and that better be the same as doing the same in the receiver's frame, right? Let me start out here. So this is eta of the emitter's frame in the emitter's frame. That's trivial, not p. But that is simply, see, this one is the trivial vector that is only the time component. So we just get e over c. Right? So this one with minus sign, this is minus e in the emitter's frame over c. Alright, but now we do this for the receiver's frame. There we have eta of the emitter's frame in the receiver's frame. P, again this was emitted, P in the receiver's frame. Well, now it becomes a little trickier, right? This is gamma C1 eta, right? That was the velocity vector. And for vector product with E in the receiver's frame over C and K. Now this is gamma E receivers. Where did I? Sorry, this is a C vector, right? Why is nobody complaining here? This is a velocity vector, right? So there's always a vector C in front of this. Sorry. So this is minus E emitters, obviously. And we have this times 1, so minus 1 plus beta dot k in the receiver's frame. But this is, so beta goes in this direction, right? Dot k goes in the direction in which the photon moves. So beta dot k gives us a cosine of the angle, so it gives us a mu, right? So we have beta dot k in the receiver's frame is simply beta times cosine of theta in the receiver's frame. So this is receivers. So what we find is that the energy in the emitter's frame is energy in the receiver's frame modulo gamma 1 minus beta in the receiver's frame. Or another way to see that, we receive the photon at an energy that is boosted by a correction factor 1 over gamma 1 minus see this frame? And this is often called the Doppler factor. It's called delta times E. So delta is 1 over 1 minus you see this is called the Doppler factor. And that, whenever you do relativistic astrophysics, Doppler boosting of photons, this is precisely the factor that's always happening. So that means, let's quickly discuss. Let's assume that gamma is much larger than 1. So beta is almost 1. Of course, has to be still smaller than 1. Let's look at the forward direction. That means we're looking at a light source that comes straight at us, and light is emitted straight towards us in the direction in which we're moving. Then this angle mu is 1. It comes directly along the x-axis. So then delta is 1 over gamma 1 minus beta. Let's do a little trick here. I just multiply by 1 minus beta on both sides. Gamma 1 minus beta squared. 1 plus beta with 1 minus beta. To a binomial formula. It's 1 minus beta squared. But 1 over 1 minus beta squared is gamma squared. So this is just gamma 1 plus beta, or if beta is almost 1, that means it's approximately 2 gamma. So photons are emitted in the direction in which we see them, in the forward direction, then we see them Doppler shifted by 2 of the Doppler factors. And in astrophysics and active galaxies or gamma bursts, we actually have emission regions apparently that are moving with close to the speed of light with Lorentz factors of 10 or so. So we actually see everything. So all the photon energies boosted to higher energies, so higher frequencies, that is blue shifted. The blue end of the spectrum is the high frequency end, the optical spectrum, so we call blue shift. So this is called blue shift. Because we are shifting energies, photon energies and frequencies to higher frequencies, to higher frequencies. If the source is moving away from us, so we see it in the backwards direction, then we see this as minus 1. Then delta is 1 over gamma 1 plus beta, approximately 1 over 2 gamma. So if the source is moving away from us, of course we see everything stretch, longer wavelength, redshift, lower frequencies, lower energy. So this is then called the redshift. Okay. Time for coffee or tea? Let's meet back here in 15 minutes, then we discuss 2 more little things and finish in the week.